Today we're going to be building quadratic functions to describe situations for the third day. And here we go. So which one doesn't belong? We've seen these things before. So we're looking at all four of these graphs. We have graph A, B, C, and D. And remember, each one doesn't belong for a different reason. So you're looking at all four of these and picking just one of them that doesn't belong. So why wouldn't A belong? And the graph is this right here. So that one, the y value doesn't change at all. It's staying constant here. Letter B, that's the only one where the y value changes at a constant rate. So these two are straight lines, but this one, the y value changes at a constant rate. Letter C, this is the only one that's not continuous. So this has each of the dots here, whereas all of these other ones are continuous functions. And letter D, this is the only one that doesn't have a y value at 2. Okay, it doesn't have a y-intercept of the point 0, 2. Now there could be other reasons why you find that those don't belong, but there's at least one reason for each of them not to belong. Alright. So, what price to charge? So with this, a company that sells movies online is deciding how much to charge customers to download a new movie. Based on data from previous sales, the company predicts that if they charge X dollars for each download, then the number of downloads in thousands is 18 minus X. So we're going to complete the table here. So this is something that is very real world. Somebody's job is to figure out how much to charge. If you don't charge enough, you're not going to make enough money. If you charge too much, people are going to want to pay for it or things like that. So let's see what we can come up with here. So remember, it is 18 minus X. Okay, I'll show that up there. 18 minus X. So if it's $3 per download, we take 18 minus that 3 and get 15. If you have 15,000 downloads times the $3, that's going to give us $45,000 in revenue. So if we have 5 here, then that means that we would have 13,000 downloads, and 5 times 13 gives us 65. If we have $10 each, that means that we're going to have $8 or 8,000 downloads. That's going to give us $80,000. 12 would give us 6,000 downloads for $72,000 revenue. The $15 per download would give us 3,000 downloads, $45,000 in revenue. If we charged $18, that means we would make, or that means that we would have no downloads at all, which means we would have $0 in revenue. So what if it was for X? We used these values. If it was for X, well, we're taking 18, subtracting it by X, and then for revenue, we have to take the price times the number of downloads. So that would be our expression for revenue. Okay? So then, is this relationship between the price of the movie, okay, so the price of the movie, and the revenue in thousands of dollars quadratic? Well, if we have X times 18 minus X, that's our expression here. If we distribute this in, so that means we would have 18x minus x squared, right? Those two things are equivalent. If we have 18x minus x squared, is that quadratic? Yeah, it's got this exponent of 2. So yes, because of the x squared term. Okay, so this is quadratic because of the x squared term. Alright, so next thing asks us to plot the points to represent the revenue R as a function of the price of one download in $X. So that means we're looking at that first column of price and the revenue the very last column on the chart. So if we're looking at this, I went ahead and already plotted those points. So this represents the 3, 45, 5, 65, 10, 80, 12, 72, 15, 45, and 18, 0. Okay, so those were all of our points there. So based on that, what price would you recommend the company charge for a new movie? So obviously, if this was connected, right, it would look something like this, where it's going to come back down around the other way, right? So obviously, as a company, do you want to make less money or more money? And for this, you want to make the maximum amount of money. That means we're looking, where is the maximum for this? So it's going to be somewhere in this area. We're not exactly sure how this connects, okay? But I would say definitely between $5 and $10. If we had to make a more accurate guess, let's say $9. Okay, so if you said $8, $9, something along those lines, probably a good estimate. Okay. All right. So then let's look at this here. So we're going to have 4 sets of descriptions and equations that represent some familiar quadratic functions. The graphs show what a graphing technology may produce when the equations are graphed. With this, though, we want to describe a domain that is appropriate for the situation. So if we graph something that's not necessarily all appropriate for the situation, we'll talk about that as we go. And we want to think about any upper or lower limits for the input, as well as whether all numbers make sense as the input. Then we're going to describe how the graph should be modified to show the domain that makes sense. So we want to identify or estimate a vertex on the graph and describe what it means in the situation. And then we want to identify or estimate zeros for the function and describe what it means in the situation. Okay, so here's our first one. The area of a rectangle with perimeter of 50 meters and a side length of x would be this equation. Okay, so the area of x would equal x times the quantity 25 minus x. And this is what it would graph if you plugged this equation into a calculator. Now, based on this, though, if we have length and area, what domain makes sense? Okay, does it make sense to have everything in the negatives here? Does it make sense to have everything up, to 50 or even 20 or 17 or 35? Like, we have to look at this. So, pretty much, we're talking about area. Can area ever be negative? No. So we don't want to look at anything that's over here, because we can't have a negative length. So we definitely want to be over here. And if we're higher than 25 here, that means that our area is starting to be negative, and that doesn't make sense either. So we would want a domain from 0 to 25. Now, why are we not including 0 and 25? Because those give us an area of 0, and that we don't want either. Okay, so that's why you do not need to put the equal to pieces there. All right, vertex, that's the place where we're changing from increasing to decreasing or decreasing to increasing. So if we follow this along, it's this point here where it's changing directions, the inflection point. Okay, so that is the vertex. We're going to estimate that to be, so, I don't know, we're in between 10 and 15, so let's say 12 and a half. And then we're estimating what that is, so it's a little below 160, so I'm going to say 155. This is also something that you could take this information, this equation, type it into Desmos, and get the exact value of that as well. Zeros, if you remember, are where they cross the x-axis. So that's going to be these 2 points right here. So we have, and actually let's just put for zeros, x equals 0, and x equals 25. So we'll just give the x values. That's what you would get if you solve this equation as well. Okay, you get x equals 0 and x equals 25. So ultimately, you would only want this space of the graph. You wouldn't want everything. Okay? Let's take a look at another one. So the number of squares as a function of step number n with our function f of n equals n squared plus 4. So again, this is graphed for us. Okay. Now, when you're talking about the number of squares as a function of step number n, remember your step number can only be whole numbers. So technically, we would just have dots here. It wouldn't be a continuous function at all. You would just need dots. If we're talking about step numbers for our domain, what step numbers do we have? Do we ever have negative step numbers? Do we have positive step numbers? Can we have a step number of 0? These are all questions you have to ask yourself. So we can have a step number of 0 if that's where we're starting. And we can have positives. So our domain is going to be x is greater than or equal to 0 because we can have 0 as a domain as a domain element. The vertex is this point here. So that would be the point 0, 4. I can see that. I don't necessarily know that that's 0, 4 there, but if I plug 0 into this equation up here, okay, 0 squared is 0, 0 plus 4 is 4. So then that's going to give us our vertex. Now this, for zeros, doesn't cross anywhere here, so we're going to say none. Okay? If it doesn't cross the x-axis, then it does not have any zeros. Okay? For this graph, again, you would only want the first quadrant because we only want positives here. Okay? All right, let's take a look at another one. So this is the third one of 4. The distance in feet that an object has fallen t seconds after being dropped. So we have the equation g of t equals 16t squared. Here's what it would look like. Okay, for domain, does all of this make sense? So we have time in seconds here and distance fallen in feet. Can you have 0 seconds? Can you have negative seconds? Can you have positive seconds? That's what you have to think to yourself. So for this, we can have 0 seconds and we can have positive. So our domain would be t is greater than or equal to 0. Your vertex is happening right there. So that's going to be the point 0, 0. And for zeros, it's crossing only at that place. So we would say x equals 0. Okay? For this one, again, you would only want the first quadrant. Negative time, negative distance fallen doesn't make sense in this situation. And so you would not need those. Last one. We have the height in feet of an object t seconds after being dropped, and our equation is h of t equals 576 minus 16t squared. So we have our graph here. For domain, what makes sense? Well, if we're dropping an object, this means we're starting from 576 feet and gravity's taking place. So we're just dropping it. This is the ground, okay? So we can't have negative, and we wouldn't want to be past 6 seconds because then that means that this object would be underground, which we don't want either. Here's our vertex, okay? And if we plug in 0 to the original equation, we would get 576 out as our y-coordinate. And then for zeros, we're looking where it crosses in the actual domain area. So I don't care that it crosses over here somewhere. This is the only 0 we are concerned with. And so then that would be x equals 6. Okay? Since we're counting by 2's there. And that's it.